Okay guys, so today we are going to learn about chapter 8, which is about torsion. Okay, so from here we go to the theories a bit. So characteristic of torsional loadings on the circular prismatic bar is observed. Okay, you can see that here is the torsions. Okay, so the longitudinal axis of the shaft remains straight. Means that the longitudinal axis, the axis here will remain straight, and then the shaft does not increase or decrease in length. The length will be the same. Radial lines remain straight and radius as the cross-sectional rotates. Okay, it will rotate. Okay, and then the cross sections rotates about the axis of the members. And then the shear stress in circular sections when the torsion happens is shear stress is equal to T R over J, where T is applied torque acting on at the cross section Newton meter. Okay, and then the R is the radius of the shaft, meaning the R's here. Okay, and then the J is the polar moment of inertia of the cross sectional area. Okay, so this is types of circular sections. We can see that here. Okay, so circular section, we know that we have solid circles and also hollow circles. Okay, and then for the solid circle, the I is pi d power 4 over 64, and the J, which is the polar moments, is pi d power 4 over 32. So this one you need to memorize. Okay, so for hollow circles, okay, actually the formulas is similar, just you need to times pi d outer power of 4 minus d inner, okay, power of 4, and then 32 over 32. Okay, and then the angle of twist, okay, phi is phi equal to TL over ZG. So phi here is the angle of twist in radians. Okay, and then the T is applied torque, and then the L is the length of member, and then the J is the polar moment of inertia from the previous I explained before for circle and hollow circles. And G is the shear modulus of materials. Okay, so normally it's Newton per meter squared. Okay, and then also we have the power transmission. So you can see that this is the theory. So the circular bars of shaft are commonly used for transmission of power. So from design standpoint, it is necessary for the shaft to be strong enough to transmit power safely without exceeding the shaft material's elastic limit. So power is defined as the work performed per unit, okay, over time. So the work transmitted by rotating shaft equals to the torque applied times the angle rotate. So the formula here is the work is equal to torque times angular displacement. Okay, so power is equal to d over dt time d over dt work. So if the torque is not a function of time, then the equation of power simply becomes P equal to TW, where P is the power, okay, Newton meter per seconds, or either is watt, and then T is applied torque acting at the cross section, and then W is the angular velocity of the shaft. Okay, we will go through more examples for the calculation for you to be familiar with all the equations I explained. And then for machinery, the frequency of a shaft rotation F is frequently reported. So this is a measure of the revolution numbers of cycles of the shaft. So just now the TW, so W is also equal to 2 pi times F. Okay, so we have the F equal to frequency, and then W equal to 2 times 2 pi F. So it is important that we use consistent unit for P, T, and W. So the power is commonly specified by horsepower, HP. Angular velocity, the W, is given in revolution per minute, RPM. If provided RPM, then we need to convert it to radians per second. So to do it, you need to convert from RPM times 2 pi over 60. Okay, so now we go for the examples. Okay, a hollow steel shaft has an outside diameter of 150 millimeter and an inside diameter 100 mm. The shaft is subjected to a torque of 35 kN, and then the modulus of rigidity for the steel is 80 gigapascal. So determine, okay, A, the shearing stress at the outside surface of the shaft, B, the shearing stress at the inside surface of the shaft, and then C, the magnitude of the angle of twist in 2.5 meter length. So what is the solution? Before we go to the solution, normally I like to list out what we have the information from the questions. So here we can know that the D out is 150 for the outside, D in is 100, okay, and then the T is 35 kilonewton meter, and then the G here is 80 gigapascal. Okay, so for the solution here they now want you to find the shear stress. Okay, this is the stress, and then for the outside and for the inside, and then the magnitude of the angle of twist in a 2.5 meter length. So this is also want to find the stress, this is want to find the angle of twist. Okay, so we know that J is equal to pi 32, the D out over D in, and D out minus D out power 4 minus D in power 4. So we substitute the value inside, we can get the value of J. Okay, so we know the stress, the shearing stress is equal to TR over J. Just now I explained this already. Okay, the equations. So T, we have 35 kilonewton meter. So here is Newton meter. Okay, and then times the R. R is 0.075 for the outer, because the diameter is 150 mm. So it's 75 mm for radius, and then you convert to meter. Okay, and then the J here is 39.89 times 10 power of negative 6. This is millimeter. This is meter power of 4. Okay, so you need to do the conversion of unit. So you get the T for outside is 65.81 megapascal. And then after that we can get the shearing stress for the inside of the shaft. So it's similar. Just now you put the R for the outside. So now you put the R for the inside. Okay, so you input the value of T, the value of R, and then value of J, and then you calculate, you can get this value. Megapascal is Newton per millimeter square, so you can convert it yourself. Okay, and then the magnitude for the angle of twist in 2.5 meter length. So angle of twist is equal to TL over JG. So you have the value of T, the length is 2.5 meter, the value of J, and then the value of G. You input everything with the correct units, then you can get this 0.027 radius.